Okay. I don't think, well, this is working. Hello, everyone. Thanks for coming to this talk. When we are going to talk about how to implement KAPPA architectures and a first approach to integrate two very important and interesting technologies to implement a KAPPA architecture, like Apache Flink and KUDU. Well, firstly, a very brief introduction about ourselves. My name is Rubén Casado. I'm PhD in computer science. Currently, I'm the chapter lead in big data here in Accenture Digital Spain. In addition, I'm the organizer of the Apache Flink meetup in Madrid and the director of the master in big data architecture in Casado.
Hello, my name is Nacho. I hope you are well and enjoying the conference. What about me? So I am an open source passionate. I really like to contribute to open source projects. In addition to that, I'm also senior big data engineer at Accenture Digital, and also lecturer of master in big data at Key School. Well, I have also a master's degree in computer science.
Okay, before going to technical details about the connector that we have developed, let me provide some details about this project, the context of why we have done this project. Well, firstly, as everyone knows, Accenture is a large company, always working with big clients, executing big projects. For example, we have ranked as the best provider of big data solutions in Spain. But behind this brand, there are plenty of technical guys, like Nacho or myself, working with the state-of-the-art technologies. So, of course, we have to work very close to the open source community, because the open source community are leading the new age of big data technologies. So we need and we want our developers to understand the importance of the open source community in the landscape of the big data. And I think this project was a clear example and a very good example of it. Well, let me say that this project was started by a junior team, actually undergraduate student that currently are working with us in Accenture. We wanted them to learn Apache Flink, to learn KUDU, but the most important goal was to encourage them to use and contribute to the open source community. Well, they made a good job. They provide a proof of concept about this integration. It was good. We wanted to use it in our clients, so we need a production-ready version. This new version is led by Nacho. The final step of this work was, or is, to contribute to the open source community. And the best place to do that is Apache Flink, which is an Apache project when you can provide extensions to different data processing engines like Apache Flink or Apache Spark. So basically, we have to follow the following steps. Firstly, we had to open a ticket Jira to describe what we wanted to contribute. After several weeks, the ticket was assigned to us, so we were able to open a pull request and send our contributions. Sometime later, we received some feedback, and currently, we are working in this new version, taking into account the feedback that we received, but also the new requirements, the new needs that we want to push. And hopefully, in the following weeks, we will send the final version to the Apache Flink, and we will integrate it in the official release. OK, let's talk a little bit about KAPPA architecture. We have been talking about big data for a long, long time. We always were talking about the three main problems: volume, velocity, and variety. We had three solutions. We had batch processing in order to deal with a large amount of data using different processing paradigms, like parallel and distributed systems. We have streaming processing in order to provide low latency real-time results. And we had NoSQL storage system to have different approaches to storage and query the information. But there was a scenario that was not solved. What about the scenario when we have to take into account a large amount of static data, but also we need to analyze the new information that is arriving in real time? Some authors call it the hybrid computation model, and I'm quite sure that all of you know the solution. That is the LAMBDA architecture. LAMBDA architecture was defined by Nathan Martin in 2011, and basically what the LAMBDA architecture say is, OK, you need two different systems. You need a batch processing system in order to manage all the information, and you need a real processing system in order to compensate the delay of the batch system. When you need the result, you have to combine the results coming from both systems. Something that we have to take into account is that the LAMBDA architecture was defined 6 years ago. On that time, there were plenty of batch technology in a production-ready version, technology like MapReduce, HDFS, Cassandra, HBase, and so on. But the streaming technologies were not as powerful as they are today. So in the incoming years, thanks to the release of more powerful technologies like Xantha or like Apache Flink, a simplification approach was proposed by Jay Cripps from LinkedIn, and it was coined as KAPPA architecture. Of course, the KAPPA architecture is a different approach. It understands the system like log-centric, and it is something similar to an open database, but at the end, they provide a result for the same problem. In a KAPPA architecture, we understand all the information like streaming data. So we need a streaming engine, and we need a data layer that allows low latency read and write operations. How we can implement a KAPPA architecture? Well, there are plenty of technologies to do that. This is a approach that we think is OK, and it's working in our projects. We need a message broker like Kafka. Kafka has a very good performance. Kafka is scalable. And something that is very important, Kafka allows replaying all the information in order to be able, with our system, to reprocess historical information. We use Flink as a streaming engine because Flink is the most advanced technology for streaming processing right now. And we thought that Apache Kudu fit very well in this approach thanks to the different features of Apache Kudu. So now Nacho will provide details about how we have connected these two technologies.
Thanks. Hello? OK. So before introducing what Kudu is and the connector that we have done, let's explain why we did it. So here in this chart, we have the y-axis that refers to the analytics performance. And well, by analytics, we mean fast scans on a lot of accumulated data. So a use case for analytics will be, for example, to make some kind of interactive query by using some kind of SQL engine like Apache Impala. And here we have HDFS with Parquet that have demonstrated that have a very good performance in this use case. But the problem is that we also have the x-axis that refers to the fast random access. Well, the problem here is that HDFS with Parquet are not done to cope up with this feature. They don't provide any indexing system, and update your records using Parquet could be a very difficult task. So here we have HBase that, let's say, provides the opposite features. HBase gives you fast random access, so you can efficiently find and update a single row, index your reads, and so on. But the problem here is that if we try to run SQL queries over systems like HBase, Accumulo, or Cassandra, the performance that we will get will be always lower than using Parquet. So if we require both use cases, both fast scans and fast random access, we need to maintain two different store layers, which could result a very hard task. So hopefully, we have Kudu here, which tries to fill this gap. Kudu, it's not better than Parquet in fast scans, and Kudu is not better than HBase in fast random access. It is just in the middle. It is just pretty good at both. So in case you have a workload that requires fast scans and fast random access, Kudu can help you to simplify your architecture by maintaining just one layer. OK, so let's say that Kudu is not a replacement for Parquet or HBase, because sometimes you will probably need the entire potential of the systems. This is just an alternative, OK? By the way, just in case that you don't trust me, in this link, you can find some benchmark that compare the performance of Parquet, Kudu, and if I'm not wrong, also Avro. And the result is that Kudu is in the middle in terms of performance. Yeah, so Apache Kudu is an open source columnar-oriented data store, and that provides a combination of fast inserts, updates, and also efficient columnar scans, okay? Tables in Kudu have an structured data model, like in the relational databases. We have fixed schemas for the tables, we have fixed types, and we also have primary keys. So this is very similar to the relational databases. Another cool feature of Kudu is that it was designed and optimized for analytics workloads. So it lacks some features like multi-row transactions or secondary indexes that are commonly supported by transactional systems. So let's be clear in that Kudu is an analytical system and not a transactional one yet. And the last feature, but not least, is that Kudu is fully integrated with Hadoop. Okay, it is integrated with Impala. We can run SQL queries over Kudu by using Impala. It is also integrated with Spark, and now it is integrated with Flink. Okay, so in the end, what Flink what Kudu is a data store designed for fast analytics on fast data. And just some concepts that we need to understand in order to know how the connector works. So the columnar data storage, Kudu provides a strongly typed columns, as you already know. The read efficiency in Kudu is a key concept because in an analytical workload, if you are using Kudu, you can read just a portion of a column, ignoring the other ones. So this means that you can fulfill your query by just reading a minimal amount of data on disk. If you are working with a row-based store, you need to read the entire row, even if you are just projecting some of them. Okay, so in this sense, Kudu has better performance. Well, all of you know what a table is. A table is the place where data is stored. In Kudu, data is split into small segments called tablets or partitions. A tablet could be replicated, so for the same portion of data, we have more than one tablet server, and then we have a tablet leader and several tablet followers. So if the tablet leader gets down, then elections are produced between the follower nodes, and then new leader is selected. It's very, very easy. We also have the master nodes that, let's say, keep track of everything. Master nodes also follow the leader-follower model. And then, well, the catalog table that is a kind of central location for metadata in Kudu. So these diagrams shows how the Kudu architecture looks like. As I said before, we have the master servers we have the server A, that is the leader one, and we then have the follower ones, okay? Server B and C. But we also have the tablet server, okay? In this case, we have 4 tablet servers, and the feature here is that each tablet server can store more than one tablet, more than one partition, okay? So in the case of tablet 1, the leader is in the server D, but we also have followers in the server E and the server F. This is how it works. And as you know, this connector is about integrating Kudu and Flink. So let's dedicate this slide to introduce what Flink is, just in case some of you don't know it. So Apache Flink is an open source streaming processing that has a common runtime for both batch and stream jobs. It's like an unified engine. It also provides high performance and low latency in your jobs. And exactly one semantics when you are dealing with stateful computations. It is also fault tolerant via distributed snapshot, and well, Flink has its own memory management system and a program optimizer that optimize your programs. So what this diagram shows is a streaming data flow in Flink. Okay, and as you can see, this is all about operators. We have three main kind of operators. We have the source operators that, let's say, get data from somewhere and get it into Flink. We have the transformation operators that modifies your data. And we also have the sync operators that take data from Flink and move it to external system or databases like KUDU. And as you know, this diagram happens in parallel. So there is not just one streaming data flow. There are several ones depending on your program parallels. So now we are going to explain what this connector is about, how it was implemented, and later on, if we are on time, we will show a little demo about the connector. So yeah, in this diagram, you can see different Flink connectors that already exist. Flink provides a connector for several systems, including Kafka, Redis, InfluxDB, Elasticsearch, and so on. And one important thing here is that Flink connectors are currently part of the Flink project. Indeed, they are a submodule inside of the general Maven project of Flink. However, it is planned to move all the connector to another Apache project called back here that Rubén mentioned before. So with this connector, we are contributing directly to the Bahir community instead to the Flink one. And yeah, you already know this Flink streaming flow. But in this diagram, you can see a little modification regarding to the previous one. The first and let's say unique thing that we made to develop this connector was to provide a KUDU source and a KUDU sync for both batch and streaming APIs. Okay? So these are the base classes of Flink that we have to implement, to use in order to develop our connector. We have two for the batch API, input format and output format, and two for the streaming API, source function and sync functions. So let's start with the input format. The input format is the base interface for data sources that produce records. Input format describes how the input is split into different splits and that can be processed in parallel, okay? So our implementation here is called KUDUINPUTFORMAT, and later on we will show an example. The same occurs in the output format. The output format describes how to store the final records, for example, in a file or in a database in this case. And here our implementation is called KUDU output format. Yeah, the source function for the streaming API. This is the base interface for all the streaming data sources in Flink. Yeah, it is in charge of producing records from an external system in a streaming fashion. And currently, we do not provide a streaming KUDU source because the change data capture feature of KUDU is not implemented yet. So by the moment, it makes no sense to add a KUDU source. We can't, indeed. And yeah, the sync function that is the interface for implementing user-defined sync functionality. Here we have a KUDU sync function that allows to write data into KUDU in a streaming fashion. Okay, this is very simple. So this table just summarizes the previous slide, just in one table. Yeah, as you can see here, we have two additional classes, the Kudu batch table source and the Kudu table sync. They belong to the Flink table API. For those that don't know the Flink table API, let's say that this is just an Scala API that allows to run SQL statements over our data sets and data streams. And well, it is based on Apache Calcit. So using these two classes, we can apply SQL statements over our data streams. We will see an example later on. And yeah, this is how the API looks like. The first step the first step is to create a configuration object by specifying the master address or addresses and the table name. Optionally, we can specify a predicate to reduce the amount of data being moved from Kudu to Flink. We can skip this step and apply filters later on in Flink, but it is usually less efficient because it requires to move the entire table from Kudu to Flink. So be careful with this. The next step is to create the execution environment of Flink, and then we create the input, passing the Kudu input format with the configuration at the first parameter. And yeah, you can see that we have a second parameter here that refers to the type information of the table. This type information should be equal to the type of the table, okay? So to the columns of the table. If they are not equal, the application will throw an error. This is needed because Apache Flink obviously is not able to infer the data schema of the Kudu table, so we need to specify this. After creating the input, we can just apply other operators of Flink, like flat map, maps, and whatever. So the previous slide showed how the API looks like, but this slide shows how it works in a lower level. Okay, so here we have a Kudu table with 4 partitions, 4 tablets, and we have also a master node, a Kudu master node. And in the other side of the screen, we have a Flink program with a parallelism level equal to 5. We also have 5 task managers, and we have 1 slot per manager. So in the end, we will have 5 parallel instances. So when the program starts, and each parallel instance creates a Kudu input format, they create a Kudu client that connects to the master node. Okay? Each of these clients can automatically configure a Kudu scanner by taking into account the user query, the table name, and so on. So then once the Kudu scanner for each instance is configured, it has the ability of reading a specific portion of data from a concrete table, if possible. So this is the way that we and Kudu have to parallelize queries. This highly increases the parallelism and performance of the application in general terms. There are many connectors out there that work in a non-parallel way, and just one instance can read data. And obviously, this is not efficient for big data. So as you can see here, in this case, we have 5 parallel instances and 4 tablets. So the 5th instance will remain idle, since it has not partition to read from. So in this case, it produces a data skew because Flink instance has not the data to work with. So we can avoid this in an easy way by using some kind of rebalance or shuffle operation in Flink. Okay. So yeah, after creating the input, we can just apply Flink operators like map and whatever. And this example is very similar to the previous one. This example shows the KUDU output format to write information from Flink to KUDU. Here we have also a configuration object with an additional parameter that is the write mode that can be insert or upsert. We then just create the execution environment and apply the output with the KUDU output format. Okay, it is very easy. So this is what is happening when we use the KUDU output format. After call maps and the output, each instance creates a KUDU client and writes data in parallel, okay, to a specific partition. And the last example is the Flink table API. In this case, we create the execution environment of Flink, but also the table environment. After this, we create the KUDU batch table source with the type information. Oops, sorry. We need to register the table with a name, and then we can apply SQL statements over the data stream, the data set in this case, okay? So I think we are on time. Let's show a little demo. I cannot change the screen. Yeah.
I don't know the problem. Well, I think we are out of time, so
yeah, we can skip the demo. And, yeah,
well, basically the demo is the code that we have shown here. As conclusion, we would like to say that using this connector, you can read from any streaming source like Kafka, process the information with Flink, and write to a KUDU table. That is the main example of a KAPPA architecture. But another interesting thing is that we can use SQL for executing executing a statement from KUDU and to KUDU, something that you can not do directly if you have to use another technology like Impala.
Yeah, no problem.
I think it's okay. If you have any questions, we will be here. We have a stand of Accenture there, so we can provide more technical details or show the demo if you want.
And just the last slide. So if you want to run the examples by yourself, here you have the connector code and the examples. Hopefully, in a near future, both the examples and the connector will be moved to the Bahir community, to the Bahir project. But meanwhile, you can use these links, okay, if you want to test it. And if you test the connector and see that something is wrong or whatever, please do not hesitate to contact us in GitHub. Any contributions are more than welcome, okay? This is not about company interest. This is about open source. So let's collaborate and make the community bigger. And just, I promised the last slide, the future work for this connector. Yeah, as a major improvement, we will support more data types. Currently, we just support tuple informations. We will also add a KUDU source for data streams as soon as the change data capture technology is implemented on KUDU. And we will fix some existing issues regarding to the limit operators. Currently, the KUDU Java scanner does not support this feature, so we cannot limit our queries before loading data into Flink. Yeah, that's all. Thank you very much.